we go to the social lecture. We will have Professor Arti Garg, who was a student in TIFR. But to introduce her, we have your community.
Thank you. This is pulling my leg. Okay, it's a great pleasure to introduce Professor Arti Garg from. Okay.
Hi, it's a great pleasure to introduce Professor Arti Garg from Saha Institute of Nuclear Physics as a special person who will give the special lecture today. Arti and I, of course, share a very long-standing bond. We have the same PhD advisor, and both were started their PhDs. She completed her PhD from TIFR. I started here and left at some point. Arti did her PhD with Professor Mohit Randeria in TIFR on high-temperature superconductors. And then she left for Technion in Israel, where she was the Lady Davis Fellow. And she worked with Professor Asa Auerbach on a variety of problems in strongly interacting systems. You have lots of quantum degrees of freedom, and they're interacting very strongly. And Arti is a great expert in looking at those kind of systems. Then she went to University of California, Santa Cruz, where she worked for some time. And then she came back and joined Saha Institute of Nuclear Physics, where she has been for now last 10 years approximately. Arti is, of course, very knowledgeable about, the strongly interacting quantum systems. Especially, she has developed certain numerical techniques, which, she's quite an expert in. She's one of the leading experts in the country in things like dynamical mean field theory and stuff like that. And she's also been recently the guest editor of famous issue of Physics News, which is going to talk about women in science and physics in India. So she has been helping with that. So with this, I would just let Arti take the stage and take you through her latest passion, which is working on Manybody. I'll let her explain what this is. It's a very complicated thing, but she's very great at explaining things very clearly. So over to you, Arti.
Thanks. Thanks, Arti, for a very nice introduction. And I would also like to thank Vandana and other organizers of the Vigyan Vidushi program, which I think is a very significant and important program. And I'm very glad that TIFR has really started this program. And I'm happy to contribute at least by giving a small lecture in this program. So I'm going to talk about something called Manybody localization. But before we go to the talk of the topic and before we start with the subject of my research, let's remember some of the very famous women in physics who made significant contribution to various branches of physics in 20th century. So I'm sure that you will be able to recognize at least one or two of these faces because their contributions are already included at the textbook level in undergraduate courses. So I'm sure all of you should be able to recognize Marie Curie for her significant contribution to radioactivity, and also Amy Noether for her work on symmetries and conservation laws. But I have added a few more names which are more significant. Their contributions are very significant as far as the condensed matter physics is concerned, which is the area of my research. Okay, so here you have Marion Ashe, who is famous for her work on semiconductors. She basically did experiments on semiconductors in very strong electric and magnetic field. And Dresselhaus, who is known as the queen of carbon nanotubes, and Barbosa, who is a Brazilian physicist, and she worked on hydrodynamics, trying to understand the role of interactions in water molecules. So the list of women who have contributed in 20th century to the various branches of physics is actually pretty big and impressive. And in interest of time, I have included very few names here just to show that women have always been contributing to the progress of science and physics, especially because this is a lecture on physics. I'm only talking about physics. And It's not something very new that we are trying to talk about, that there should be women in physics. There have been women in physics, but unfortunately, the fraction has been much smaller than it could have been. Now, coming to the Indian women in physics, again, we have a pretty big and impressive list. I'm just flashing some names. Okay, so Vijaya Lakshmi, who is famous for her work on relativistic wave equation, Anna Mani, she was the first woman scientist to do her PhD with C.V. Raman on atmospheric physics. Radha Balakrishnan is at IMSC, she works on nonlinear dynamics. And I have included a name, Kamla Sohni, who is not a physicist. She did her PhD, she did her research in biochemistry. But when we are talking about women and science in India, I think it's very important to talk about Kamla Sohni because she was the first one who started research at Indian Institute of Science in 1933. And at that time, the then director, C.V. Raman, was somehow not very convinced that women can do great in science, but her hard work and passion made him change his mind. And after 1 year of her research work, a regular research position for women in science was started at the Indian Institute of Science, Bangalore. So I think all of us should be very grateful to Kamla Sohni because of her hard work and passion, because it changed the way science was done in Indian Institute of Science, Bangalore, and also in India overall. So coming back to the topic of my research, so I'm basically a condensed matter physicist. And I think condensed matter is the most interesting branch of physics, which deals with various kinds of interesting and exotic phases of matter and the phase transition among these phases. So here I have listed some of the most interesting phases that we come across in various experimental samples. For example, superconductivity, superfluidity, Mott insulating phase, half metallic phases, magnetically ordered phases, quantum spin liquids, and so on. So the list is much bigger again than what I'm showing. And there are two very key ingredients which are necessary to realize any of these phases. First is that the basic degrees of freedom are quantum. They are not classical degrees of freedom, but they obey quantum mechanics. And the second thing is that these degrees of freedom are not just lying around in a non-interacting fashion. They are strongly interacting with each other. So it's very crucial to have interaction among basic degrees of freedom and have the principles of quantum mechanics in order to realize all these interesting phases of matter. Now, if you look at these phases, for most of these phases, the basic degree of freedom is just an electron, which is a spin half fermion. Now, it will be, of course, very interesting to ask how these electrons can give rise to so many different phases. It's just a charged particle with some finite mass and a spin half. If you just have a non-interacting electron, of course, you will only get a Fermi gas, which I'm sure all of you have studied in your statistical physics course. But when you make them interact in a very special manner, which happens in various materials and systems which can be prepared in lab, then new physics and new phases of matter emerge. Okay? And all this can be put together in a very nice quote, as was always said by Phil Anderson, who is a Nobel laureate, and actually who had contributed a lot to the field of condensed matter physics. So Phil Anderson always used to say more is different. So if you just take one electron, of course, it is just an electron. You can't even define the temperature of that electron. But if you put many of these electrons together and let them talk to each other, then amazing things can happen. You can have superconductivity, you can have Mott insulating phases, you can have half metallic phases, all sorts of interesting phases of matter can appear. And these are not just theoretical concepts. These are the things which we see in labs thanks to our experimental condensed matter physicists who come up with these interesting materials and phases every day in lab. And it's really amazing to try to understand the mechanism behind the formation of these phases and how the phase transition between different phases takes place. So today I want to add one more interesting phase of matter, which is Manybody localized phase, to this very well-known list of phases, which I'm sure you have already heard about. But before I do that, let's just try to see what is the role of interactions in some of the phases that I have mentioned. So let's talk about conventional superconductivity. So all of you know what is conventional superconductivity, I guess. Are you guys familiar with superconductivity? Very good. So at least some of you are saying yes. So I assume that all of you are familiar with superconductivity. So in a superconductor, below certain temperature, the resistivity of the material is zero. And another interesting characterization is that it expels a magnetic field and it's a perfect diamagnet. Okay. Now, both these properties are very interesting if you try to think about. Even in your normal copper wire, you have the same electrons moving around, but you have finite resistivity. That's why your wires become hot after when you pass current through them for some time. But then we have these amazing materials for which the resistivity is zero below certain temperature. So how can it ever happen that you have so many electrons moving around in a system? They must be hitting with each other and all sorts of things must be happening. And still the system manages to have zero resistance to the flow of charge. Now, the way it happens is that, so if we talk about the conventional superconductivity, the way it happens is that every electron, because of the electron-phonon interaction, doesn't feel repulsion of another electron, but it feels an effective attraction towards another electron. And that's how electrons form pairs, which are known as Cooper pairs. Okay. And then we have a very coherent soup of these Cooper pairs. So these Cooper pairs move in a coherent fashion in the system, and there is no resistance to the flow of charge. It's not the electron which is trying to move around, it's the Cooper pair together. So lots of Cooper pairs move in a very coherent fashion such that the resistivity of the system is vanishingly small. And this persistent current produces a magnetic field which opposes the externally applied magnetic field and makes this system a perfect diamagnet. And both these properties are very important and essential, and they have applications not only in physics, but even in medical science, transportation, and at many, many other places, which I'm sure all of you know. There is another class of superconductivity which goes with the name of high temperature superconductivity, which is very close to Rasdeep as well as to me because we started our PhDs with that. And so what happens in this kind of superconductor? There are at least hundreds of materials which go under the name of high temperature superconductivity, and all of them satisfy qualitatively this kind of phase diagram, that the parent compound is an insulator. Okay, so it is something which cannot conduct charge at all. And when you do something to that material, when you remove some electrons and add some holes into the system not only starts conducting, but it becomes a superconductor. Okay, so it looks like something completely unbelievable that you start with a system which cannot conduct at all, which is an insulator. You add some holes into the system. Basically, you remove some electrons from the system and it becomes a superconductor. Okay, so how can it ever happen? So let's first try to understand very quickly what is this insulator, because the role of interactions is already encoded in the physics of this insulator. Okay, so just to give you a very simple picture, if you think of a system where you have as many electrons as the number of sites in the system, then according to the band theory, this system would have been a metal because your band is partially full and it's possible to create particle-hole excitations across the Fermi energy, and these low energy excitations are the one which help your system to conduct. Okay, so this system should be a good metal. But then that's not the complete story. In these systems, which I talked about, with these high temperature superconductors, whenever two electrons are sitting very close to each other, it costs a large amount of energy, which I'm calling U here. Okay, so whenever two electrons are sitting very close to each other, it costs a large amount of energy. So that is why now you can imagine if any electron tries to move on any other side, it will result in the formation of two electrons on that side, and which is energetically not favorable. So nobody will move. So everybody is basically just stuck in their seat, and the charge is completely frozen, and the system is basically an insulator. Although if there are no interactions, the same system should have been a very good matter. Okay, so interactions can make a system insulator. It basically opens a gap in the single particle excitation spectrum, and unless you provide an energy of the order of U, the system won't be able to conduct. Now, so this is the story of this Mott insulator, and there is another interesting feature that these electrons can gain little bit of energy if they are not parallel, but they are anti-parallel, because they can at least virtually hop and sit together on some site for a very, very short period of time and then come back, because that is allowed by Pauli exclusion principle. If they are all parallel, then even virtually they cannot hop. So that's why the electrons are not either randomly arranged or their spins are not parallel, but they form singlets, and the system goes into what we call an antiferromagnetic magnetically ordered state, where the spins are anti-parallel to each other. Okay, so the charge is completely frozen because you have very strong electron repulsion, and the electron spins are basically forming a macroscopic singlet. So it's a quantum Niel state. Now, how do we get superconductivity in this system? Now, if you do something to remove some electrons from the system, it basically means that you have added some holes into this lattice. Then, of course, these electrons can move, because it will not lead to any formation of doubly occupied site. Okay, so this system can conduct, but something more interesting is happening, that because of the spin fluctuations of the electrons, there is a glue between the electrons which help in the formation of Cooper pairs again. And again, in this superconducting phase, you basically have a very phase coherent soup of Cooper pairs, which gives rise to superconductivity. When you go above, as you increase the temperature, what happens is you still have Cooper pairs, but then the Cooper pairs don't move so coherently. So they lose the phase coherence, but there are Cooper pairs. So this is the pseudo gap phase. And if you go to very high temperatures, it will just become a metal, because even the pairs will break. Okay, so this was just to give you an example of that how strong correlations between electrons can give rise to amazing phases of matter. It can make something insulator, which would have been a metal without interactions. And on another side, these strong correlations can also make something superconducting, which would have been only a normal metal. Okay. Now, another example of what interactions can do is interactions can also make only one of the spin channel of the electron conducting and the other channel insulating, resulting in something called a half metallic phase. And these kind of materials have a lot of applications in spintronics. Okay, so interactions can give rise to various kind of interesting phases. Now, another important aspect of all condensed matter system is disorder, dirt. Basically the impurities. Okay, so every kind of sample you try to make, if you talk to your experimental friends, you will see that there is always some kind of disorder into the system, some kind of defects, some kind of impurities, vacancies, and all sorts of things are there. Okay, and we do know that these things are there because we have experimental tools to see that many systems, for example, these are the pictures for high temperature superconductors that I just talked about, they can have inhomogeneity even at the microscopic scale. Okay, so there are impurities into the system, and most of the time we think very negatively about this disorder. But the interesting thing that I'm going to talk in this seminar is that disorder can also lead to novel phases of matter. Okay, it can make a quantum particle localized, and that's what we are going to discuss now. Okay, so the physics of localization, the story of localization actually started way back in 1958 with a very seminal work by the Nobel laureate Phil Anderson. And in this work, what he said is, think of a quantum particle moving around in a random medium. As the quantum particle moves around, it keeps hitting the impurities, and because of repetitive scattering with these impurities, this particle may not be able to diffuse across the system. It may get localized. Okay, so, and if the system doesn't have diffusion, it is basically an insulator, because we know that conductivity is proportional to the diffusion coefficient. So basically, you don't have any kind of interaction in this system. You just have some single quantum particle, but there are lots of impurities in the system. And as the particle is moving around, it keeps hitting these impurities repetitively, and the system may become diffusionless. This is what we call Anderson localization. Now, what was surprising about Anderson localization? Now, the surprising thing about Anderson localization is because 50 years before Anderson, Einstein told us that if you have a classical random walker and you look at the motion of this classical random walker, then the displacement of the walker will basically obey diffusion equation. Okay, so the mean square displacement of the walker is always proportional to time. But now, 50 years later, Phil Anderson showed that if you have a quantum walker, then it can happen that the system will not have any diffusion. Okay, so D can be 0. So what is the difference between this classical random walker and quantum random walker? Classical random walker is basically a Markov process. It has memory of only one step. It doesn't know what happened 5 steps back. Okay, it only knows about where it was 1 step back. But when we are talking about a quantum walker, so quantum mechanical system has memory inbuilt because of the physics of interference. When a particle goes and comes back, then the phase that trapped, that depends, that's the property of the interference, and the system knows from which path it has traveled to come back to that point. So it has a long time memory, okay? And this makes the physics of the quantum particle very different from that of a classical random walker. So in quantum mechanical system, it is possible that you have a particle doing a random walk and the system may become diffusionless. So how do we understand this Anderson model? Now, if you don't know this, if you cannot understand this equation, just forget about it. What I'm trying to say is you just have some hopping of some particles from one side to another. And another term is that every site you have a random disorder potential, okay? Because I want to mimic a system which has randomness in it. That is what Anderson was studying, and that is what is essential for the physics of localization. So if you don't have this term, if you just have the hopping of particles from one side to another, then of course you have nice block waves and you have extended states. All your wave functions will be extended in the entire space. But if you don't have this hopping term and you just have a local random energy at every site, of course all the particles will be localized, okay? So as you tune the strength of this disorder compared to the hopping, you of course expect a transition from extended to localized states, okay? And how does these localized states look? That if you look at the wave packet, then it will be peaked at certain point where it is localized, and then it decays exponentially away from that point. But it is important to keep in mind that this Anderson localization cannot happen in any dimension. So dimensionality plays a very crucial role, okay? But before I go to the issue of dimensionality, since I have already talked about 2 types of insulator by now, Mott insulator and Anderson insulator, so let's try to just remind ourselves what is the difference between these type of insulators. So in Mott insulators, we were not able to excite single particle excitations because there was a large energy gap in the system. In Anderson model, there is no gap opening up in the system. But because of lots of impurities in the system, the wave function is getting localized. Basically, the states are getting localized. And that is why the system is not able to conduct. So that's what I'm trying to show here. If you have an extended state and you try to look at the probability of finding a particle at certain site I in the lattice, it is more or less uniform when it is extended. And as you increase the strength of the disorder, it basically reduces and the particle gets localized. Okay, please feel free to stop me and ask questions if I'm going fast. So, but it's not that in every dimension we are going to see the physics of Anderson localization. Dimensionality plays a very crucial role. So, sorry. So, in 1 and 2 dimension, all the single particle states are localized. But if you are in 3 or higher dimensions, then the system can have a transition from extended states to localized states. Okay, so only in lower dimension, the system, all the states are localized. And that's easy to visualize because the effect of hopping is limited in lower dimension. Larger is your dimensionality, more is the impact of hopping. And that is why there can be a transition from localized state to extended states if you are in higher dimension. But in lower dimension, all the states are localized. Okay. So how this transition happens in a three-dimensional system? In a three-dimensional system, if you have no disorder, then suppose all the states are extended. But as you increase the strength of disorder, you will see that some states are localized and some states in the middle are extended. And then you increase when you go to very large disorder strength, all the single particle states can get localized. Okay. So the system has some characteristic energy scales that distinguish between the localized states on the edges of the spectrum and the extended states in the middle of the spectrum. So if your Fermi energy is somewhere, so if all the states are localized, of course, at all temperature, your conductivity is going to be 0 because none of these states can diffuse, none of these states can conduct charge or energy. But if you have some states localized and some states which are in blue extended, then it can have a different behavior where the conductivity will slowly increase with temperature. And if your Fermi energy is surrounded by the extended states, then of course, the conductivity will be finite even in the t going to 0 limit. But this is in this story, I have excluded something. I have excluded the fact that the electrons can have interaction with phonons at finite temperature. Once you include the interaction of electrons with phonons at finite temperature, then there can be, with the help of phonons, electrons can actually hop from one localized state to another localized state. So you can have, like, you can think of, steps, and each step is a localized state. But with this phonon can provide you sufficient energy to hop from one localized state to another localized state. And even if the system has all the states localized, the electron phonon mediated hopping can help the system to conduct. Okay. Shall I go ahead? Is it making sense? Okay. So now what we do? So far we talked about Anderson localization, where we just have a single quantum particle surrounded by lots of impurities in the system. But now you ask the question, what happens when you have lots of quantum particles surrounded, moving around in this random medium, and these quantum particles are also interacting with each other. They're also talking to each other. Okay, so when you turn on the interactions, will the Anderson localization or some version of the localization will survive or not? That is the question. Okay, so just as I told you that when you have interaction between electron and phonons, the system can have finite conductivity even when all the states are localized, right? So people kept thinking for a very long time that even if you have electron-electron interactions, it will help in delocalize the system, and the system should not have localization. Okay, but that is not true. Only very recently we know that if the electron-electron interactions are there in the system, as long as they are perturbative, they are weak, it is possible to have localization in many-body eigenstates. And this is what we call many-body localization. So localization can survive even in the presence of interactions. And this is what we call many-body localization. But this many-body localized phase is very different from Anderson localized phase. Okay? And how it is different, let us try to understand that. So how do we understand localization in the presence of interactions? Okay, so now think of a lattice. You have some n sites, and you have, say, some n/2 number of particles in this system. Okay, so almost at every side you have some particle or other present, and I want to study the localization of the eigenstates of this system, of this interacting quantum system. So basically you have to solve the time-independent Schrodinger equation for this n particle system and try to see what are the properties of the eigenvalues and eigenfunctions of this n particle system, right? And all of you know what is the Schrodinger equation, right? So you basically have to do that. Now, once I get the eigenfunctions and eigenvalues by solving the Schrodinger equation for this n particle system, how will I see whether these states are localized or not? So if you remember, for the single particle system, we were looking at mod psi I square in the real space, where I is the site. So I could see where my wave function is peaked and where the wave function is vanishingly small in the real space, because I had only one particle. So the probability of finding the particle is large at some place where it is localized, and away from that site, the probability of finding the particle was small. But now I have n number of particles, almost as many particles as the number of sites. So somewhere or other particle has to be there. Okay. So then I cannot look at the wave function in real space and try to see whether my system has localization or not. So I have to go to a different picture, to a different space. Okay. So suppose you have 4 sites. Let's say, suppose you have 2 sites, okay? And now I see whether there are particles or not on these 2 sites. So if there is a particle, I put a 1 there. If there is no particle, I put a 0 there, okay? So you can have particles on both sides. You can have 1 particle on one side, no particle on the other side, and so on. So you will have 2 to the power 2, 4 possibilities for this system, right? So these are the 4 corners of your 2-dimensional cube or a square. If you think of a 3-particle system, if you have 3 lattice sites, again you will get 8 possibilities, 2 to the power 3, 8 possibilities. So your, what I call the Fock space, is actually a 3-dimensional cube. Okay, and if you are thinking of a 9-side system, your Fock space will be a 9-dimensional cube, and so on. Okay, so this is the space, this is the graph now on which we can try to study whether my wave functions are localized or not, because these are the possible configurations for my system. If I'm starting with n particle system, n site system, then I have 2 to the power n possible configuration, because at every site I can have a particle or I may not have a particle. So at every site I have 2 possibilities. So I have 2 to the power n total possibilities, which means my Fock space is a n-dimensional cube. Okay, so in that n-dimensional cube, I have to see how many vertices of that cube are occupied when I look at certain eigenfunction. Yes. Suppose you go back to the first statement where we consider a system of 2 sites. Okay, now at every site you have 2 possibilities. Either you have a particle or you don't have a particle. So for 2 sites, how many possibilities will you have? 2 into 2, that is 4, right? So I can extend this statement, generalize this statement, and say if you have n sites, and since there are 2 possibilities at every site, the total number of possibilities for an n-site system is 2 to the power n. So all these possibilities, 2 to the power n possibilities, are basically the possible configurations for my n-site system, right? And these possible configurations are nothing but the configurations of my Fock space. So in short, I can say if I have an n-site system, I have an n-dimensional cube as the Fock space. That's what I'm saying. Well, it's just easy to identify because the number of points on the Fock space is exactly equal to the number of vertices you will have on the cube. Right? So basically the point is your Fock space will have 2 to the power n number of points if you have n sites. Okay. And now in this Fock space, you have to calculate when you calculate your wave function, you have to see how many points in this wave space are contributing to your wave function. Okay. So if a large number, if a significant fraction of points on the Fock space contribute to your eigenfunctions, it means that state is extended because it has contribution everywhere. But if suppose it happens that out of 2 to the power n points in your Fock space, only a very tiny fraction of the configurations contribute to certain eigenstate, then that eigenstate will be localized because it is not getting, it's very similar to the non-interacting picture where we were looking at the wave function in real space. There I was saying that most of my lattice sites are not contributing to my wave function. Here I'm saying most of the configurations in the Fock space are not contributing to my many-body wave function, because now we are talking about n particle, large number of particles which are interacting with each other. Okay. So that's how we can very simply see whether my state is localized or extended. Now, what will happen when you have a system, when you have a strong enough disorder, that a large fraction of many-body eigenstates will get contribution from only a tiny part of the Fock space, and they will be localized. Okay. Now, what is weird about it? Is there something weird about it? So you have an interacting system, and this system is able to span only a part of the Fock space, or which is the phase space basically for this quantum system available to it. Okay. So there is some very important concept in thermodynamics which we have all used, which is called the ergodicity hypothesis. So when you use statistical physics, right, when you use microcanonical ensemble or canonical ensemble average, you use the fact that your system is able to span almost all the points available to it in the phase space. Such a system is called ergodic. You start from any point, the system will be able to span almost all the points in the phase space. But if you have a system which cannot span all the points available in the entire phase space, then it is non-ergodic. Okay. So the situation we have here is that if I take certain n-site system and I say that my many-body wave functions in the presence of strong disorder are localized in this Fock space, it basically means they are non-ergodic. Okay, so I have a generic interacting system which is non-ergodic. Okay, now what happens with that? Now think of a very simple problem which you all of us have looked at. If you take a glass of water, put a drop of ink in it, what happens after some time? The ink will diffuse around and the entire water will become same color, which is the color of the ink. Now, why it is happening? Because after a certain time, the system has forgotten where did you put the ink drop. And the entire system is able to basically get almost uniform concentration of the ink. But if your system is many-body localized, which is not able to span the entire phase space, it just lives in certain sector of the Fock space, then it will not be able to do this. You start your system in certain initial condition and let it evolve. Even after a long time, the system will remember where you started with. It won't be able to forget about the initial state in which the system was prepared. Okay, so basically my system will not be able to thermalize. Yeah.
In last slide, you said that for n particles, our Fock space will be n-dimensional. So, as written n fermion. So, if my particles are fermion, so will it put some constraint or limitation on the dimension of the Fock space?
Yeah, so I was giving example of a very simple system where at every site you have two possibilities. Either you have a particle or you don't have a particle, right? So if this cube picture is confusing, then forget about it. So if you have two possibilities at every site, then for an n-site system, of course, you have 2 to the power n total possibilities, right? That's the only thing I'm saying. So that's the volume of your Fock space, right? Is it clear?
So I want the change. What would be the change if I'm talking about the fermions? So if my particles are fermions, how Fock space will change?
So if you're talking about fermions which have spin half, right? Then of course I need to add this extra spin degree of freedom, right? Then for every spin degree of fermion with say upspin, I can say whether there is a upspin fermion or not. So I have two possibilities for upspin fermion. Then similarly, I have two possibilities for downspin fermion. So total number of possibilities will become 4 at every site rather than 2. And then if you have an n-site system, your Fock space will be 4 to the power n dimensional rather than 2 to the power n dimensional. Okay. Any other question?
Example of this system.
Ergodic system. So almost everything that you see around most of the system is ergodic. For example, air in this room is ergodic, right? It is almost spread around uniformly in this. Okay, there can be some density difference because of the gravity, but still it is ergodic, right? But there are very special systems which are not ergodic.
I want to ask that.
Yeah.
Not ergodic.
Counter example. So counter example is something which I have given. So it's not easy to come up with systems which are not ergodic. Okay. So you are basically forcing the system to be in such a state so that it cannot span the entire phase space available to it, right? So you have to put some constraints into the system. And that constraint is coming here because of strong disorder into the system. The disorder is making the wave many-body eigenfunctions localized in the Fock space. And those localized wave functions are, of course, getting contribution only from a tiny part of the phase space, and they cannot span the rest of the phase space, right? So this is an example of non-ergodic. You can also do something else. You can, for example, if you're familiar with spins, you can go to certain symmetry sector of that Hamiltonian. Then within that symmetry sector, it is ergodic. But if your system doesn't talk, one symmetry sector doesn't talk to another symmetry sector, that also leads to ergodicity breaking. Because if you prepare your system now in one symmetry sector, it will remain all the time in that symmetry sector, right? And it will never go to the other symmetry sector. That is another way of breaking ergodicity. We call these systems integrable systems in physics, okay? So what we have learned so far, that if you have a disordered interacting quantum systems, we have to face a very peculiar situation where the system is interacting and still it is non-ergodic, and that is why such a system will not be able to thermalize. Okay, so why I'm saying so if you think of an isolated system, right? Generally, a part of the system can thermalize with the rest of the system acting as its bath. So B can act as a bath for A, and that's how the entire system can thermalize. That is why we are able to use microcanonical ensemble, which is for isolated systems. Otherwise, we should not use microcanonical ensemble. But this will happen only if my system is ergodic. If I have a non-ergodic system, then part of this rest of the system will not be able to thermalize a small part of my system. And the system will remember always from what we did with it some time back. Okay, it will not be able to thermalize. And that is what people have seen in experiments. These are very special cold atom experiments where you can prepare traps and put particles in a very special fashion. So suppose you have particles only on even number of sites, and there are no particles on the odd number of sites. Okay, so you have this kind of state, 1, 0, 1, 0, 1, 0. Alternately, the sites are occupied. That's my initial state. Now I switch off this trap, let the system undergo a unitary time evolution, which we always do in quantum mechanics. Okay, and the Hamiltonian of the system is such that it has a strong disorder as well as interactions among these particles. Then what will happen? If you don't have disorder in the system, then of course the system will forget about this initial condition that it had particles only on the even number of sites. Okay, and after a long time, you will see almost a uniform occupation on every trap. Okay, this is what happens when your system is extended and ergodic. Although there is disorder in the system, but it is not strong enough to localize your system, your eigenstates, and that is why after a long time, system has completely forgotten where it was initially and the system is thermalized. But if the disorder is very large, then even after a long enough time, the system will remember where we started, and that is why the occupancy is always larger on even number of sites compared to the odd number of sites. And this is a real experiment, okay? And the way people quantify it is that you can measure the difference of the occupancy on the even and odd number of sites and plot it as a function of time. So if the system is ergodic and extended, you will see that this difference, which they are calling imbalance, will go to 0 very quickly. But if it is localized, it will remain very close to 1 even after a long time. It never decays. Okay, this is how we see whether a system has any indication about the possibility of many-body localization or not.
What is the disorder over here in this? Where is the disorder in this?
Oh, the disorder was actually added with the help of lasers. Okay, so one is this trap. So basically they have two set of lasers. One set of laser will provide you this staggered potential, because of which they can prepare the system in the initial state as 1010. And another set of lasers can provide you a random potential. Then they switch off one set of lasers, the trap is switched off, and the system can evolve. System behaves almost like an isolated system, at least for short enough time. And within that time, it can undergo a unitary time evolution with respect to this disordered interacting system. Okay, so I think I will skip this part in interest of time because it's a little bit complicated. Okay, so I have told you so far three very important characterizations of a many-body localized phase. One is that the eigenfunctions are localized in something called a Fock space, not in real space. And as an effect of that, the system is non-ergodic rather than ergodic. And because it is non-ergodic, it has long time memory of the initial state and it cannot thermalize. Okay. Now, another interesting property is that if you look at eigenvalues of this system, that also has information about whether the system can be localized or extended. Because if you have weak enough disorder, it is just a random matrix, some matrix which has random entries everywhere, and it obeys certain kind of probability distribution for the spacing. You look at the spacing between consecutive eigenvalues, and what you see is that the distribution will have certain form, that the probability of having zero spacing is 0. It means there is always a finite spacing in the system between the eigenvalues. But if you have very strong disorder, then the probability distribution is different. It's Poissonian. So not only by looking at the eigenfunctions, but also by looking at the eigenvalues, we can try to see whether the system is ergodic or non-ergodic. So this is the list of characterization which I have told so far. There are many other properties which we can use to distinguish between delocalized states and many-body localized states. And if you use all of them, a generic phase diagram that you get is something like this, that if for a fixed strength of interaction, you increase the strength of disorder, first your many-body eigenstates on the edges of the spectrum get localized, and then you need a much larger strength of disorder to localize these states in the middle of the spectrum. And by the time you reach this value of disorder strength, all your eigenfunctions have been localized, and this is a fully many-body localized system. Okay? So this is a generic phase diagram. Now there are lots of open questions in this field, like what is the nature of this phase transition? What is the nature of this phase transition? And do we have some characterizations which are more easily measurable in lab compared to something like statistics of the eigenfunctions? I cannot measure eigenfunctions in lab, right? I can only calculate it. I can solve the Schrodinger equation, find out the probability density for every eigenstate, but I cannot go and measure them in lab. So do we have characterizations for this phase which are easily measurable in lab? That is one open question. Second is, what is the nature of this phase transition? Okay, so how much time do I have, Vandana? Another 10 minutes, okay. So let me first try to answer that. Can we think of some of the characterizations which are more easily measurable in lab? Okay, so generally in condensed matter physics, how do we try to find out something about a system? You have to probe the system, right? either to measure its conductivity or susceptibility, or even to find out what kind of low energy excitations that system has, right? So single particle excitations, the low energy excitations are one of the most useful tools in condensed matter physics. If the system is metallic, it is very easy to produce low energy excitations. You can just take electrons from the occupied part of the Fermi sea, put them above the Fermi sea, right? That's how you create particle hole excitations in a weakly interacting or non-interacting Fermi sea, which is basically a metal. If you have an insulator, you have a gap around the Fermi energy, and unless you provide an energy of the order of the gap, you cannot create any particle hole excitation in this system. So these singles can be measured using angle-resolved photoemission spectroscopy, where you shine light, knock out an electron, measure the momentum and energy of that electron, and then you know what is the low energy excitation that I have produced in the system. Or you can also do something called scanning tunneling spectroscopy, where you have a metallic lead coming close to the sample you want to study. And when there is an overlap of electron between the lead and the sample, you will see a finite conductance. Okay, so this conductance will basically tell you how many states or how many energy states are available at certain energy in your sample. So it gives you a measure of the density of state of that system, basically. So we really have tools for studying single particle excitation. So can we use single particle excitation for a many-body localized system? Okay, can we try to see through the lens of single particle excitations what is happening across this? Okay, Dirac material I have skipped for the time being, but it's a very special dispersion. Okay, so Dirac material, have you heard of graphene? Yes. So there are certain special materials where, because of the geometry of the lattice, okay, the low energy spectrum is linear in momentum rather than quadratic in momentum. See, most of the system we study, right, when you look at the low energy excitation spectrum, you will see that E is proportional to K square. It's quadratic in momentum. But on certain special lattices, you have a linear dispersion. These are the Dirac material. But even in those Dirac material, you can actually take out an electron from the filled part of the sea and put it above the sea and create single particle excitations. Graphene. And there are many other materials, okay, which fall under the category of Dirac material. So can we use single particle excitations, something which is very simple in concept, to understand many-body localization transition? Okay, so again, for this interacting disordered quantum system, you have to calculate, you have to theoretically find out how can we study single particle excitation. So we have developed a recipe which can be used to look at the single particle excitations in this system. We can calculate how many single particle excitations are there at certain energy. We can also find out what is the lifetime of these single particle excitations, for how long these single particle excitations going to live in my system, or how easily they can be killed. Okay, so these are the two things I'm showing here. The details are not important, but what happens is, if your system is extended and you create a single particle excitation in your system, even this excited state with this extra single particle will be able to propagate through the system, because it will have overlap with a large number of many-body eigenfunctions in your system. That is why we will be able to typically generate a large number of single particle excitations if the system is delocalized. But if the system is localized, right, I start with a localized state and I try to add one extra particle to that system. Even this excited state will be localized. It will have overlap with a very tiny fraction of eigenstates. That is why this excitation will not propagate freely in my system. It will have a very short lifetime and it will die out very easily. Okay. So this is what we tried to see, that one can find out by looking at single particle excitations. If you have lots of single particle excitations in the system, it means that it is ergodic, extended. But if your single particle excitations are exponentially suppressed, then it is basically a many-body localized system. Okay. Now, another thing is, let me try to tell you very quickly what is peculiar about the nature of the phase transition. Okay, so we have a phase transition from some extended many-body extended states to many-body localized states. So here you have ergodic states, here you have non-ergodic states. Now, what is peculiar about this phase transition? Now, to understand that, first let us recall what do we already know about phase transitions, okay? So we know about simple quantum phase transitions where I can tune a parameter in the Hamiltonian, go from one ground state of the system to another ground state, right? I can go from a ferromagnetically ordered state to a paramagnetic state. I can go from a metal to an insulator by changing a parameter in my system. So these are quantum phase transition, going from one ground state to another, which is decided by the energy of the system, ground state energy of the system. Another kind of phase transitions, Another kind of phase transitions that we know are thermal phase transitions, where the entropy is deciding what is happening as you increase the temperature, and you go from one finite entropy phase, one phase which is obeying volume law of entropy, to another phase which is also obeying volume law of entropy. Okay, so here we have both sides ground states, here we have both sides high energy states. Okay, and then generally we have local order parameters, and by looking at the local order parameter, we know if there is a continuous change in the order parameter, it's a second order phase transition because it is related to the singularity in second derivative of the free energy of the system, or it is a first order phase transition if there is a jump in the order parameter because it is related with the first order derivative of your free energy, right? We also have something very peculiar, which is known as Kosterlitz-Thouless transition, where the correlation function on two sides behave very differently. It has an algebraic decay on one side and it has an exponential decay on the other side. So this is a different class of transition, doesn't fall into this class of transitions that I'm talking about. But if we try to see this transition from delocalized to localized phase, right? Here we have a phase which is ergodic, here we have non-ergodic. Here we have entanglement entropy, which is very slow, very low, which is area law basically in scaling, and here we have volume law of scaling. So we basically, and we don't have any local order parameter, since the system is non-ergodic, I cannot even define free energy for this system. So I basically cannot use any of these tools which we learn in standard statistical physics to characterize this system. So how do I find out what is the nature of this transition, right? So how do we find out? This is a very technical slide. If you don't understand, just forget about it. I'm just going to quote a criteria because this is something which is very interesting and very strong criteria, and it's very general, okay? So these four people, and one of them, the first author is a female. That's another reason I wanted to quote it. And she's now a quantum information scientist, a data scientist. This was her PhD work, and it appeared in Physical Review Letter. And so what they said is, if you think of a system which has randomness, quench disorder in it, and if the system undergoes a continuous transition, and if there is a characteristic length scale which diverges like this, one by some parameter, transition disorder parameter W, minus WC is the transition parameter, and nu is some exponent, okay? So if my correlation length diverges like this, and if the system is undergoing a continuous transition, then this exponent must satisfy certain inequality. Okay? Now, this is a very generic criteria, and one can probably check for this criteria and see whether my system, many-body localization, satisfy this criteria or not. So we will have at least one handle to see whether my phase transition is continuous or not. But the biggest lesson to learn is that we have a phase of matter, we have a phenomena which is basically challenging all the foundations of statistical physics because it is not ergodic. We cannot define temperature, we cannot define free energy, I cannot use canonical ensemble, microcanonical ensemble, anything. So you have to come up with new tools to study this system. Okay, that is what I'm trying to say. So this slide I will skip. Then there are also issues about whether many-body localization can survive in the presence of long-range interactions or not. Okay, so I'm telling you all these issues in the hope that very soon some of you will start your PhDs and at least 1% of you will be working in condensed matter physics, and you may go up and try to look at many-body localization as your and at least some of you will be looking at many-body localization as your PhD problem. And so you should know what are the open questions. If I just tell you what is the story, what has been done, then there is nothing interesting about it. Okay. So we don't know whether exactly what kind of system these many-body localization can survive. If we have long-range interactions in the system, will it survive or not? Why do we think so? Because suppose you have long-range hopping, right? If I have very long-range hopping in the system, then of course the system will delocalize very easily. Will the same thing happen if you have long-range repulsion also between fermions, for example? If I take a strongly disordered system and rather than having some short-range repulsion between the fermions, if I have very long-range repulsion between the fermions, will it delocalize the system, or is there still a possibility of seeing many-body localization in certain parameter regime of the system? Okay, so that is something also we studied, and I can tell you the answer we have, that if you have very long range hopping, of course the system will delocalize. But if you don't have long range hopping, but you only have long range repulsion or between the fermions, it can still remain localized. Okay, but this is still an open question because we don't have a mathematical proof for many-body localization in the presence of long range interactions. We have a mathematical proof only for one-dimensional system in the presence of short range interactions. So, but there are experiments, sorry, I should mention, there are experiments which are done with trapped ions again, and there people have been able to go to very long range interactions, and they have seen some signatures of many-body localized phase. Okay. But again, these experiments on trapped ions are again done with a small system size. It's not possible to trap lots of ions, and that is why we really don't know for sure whether many-body localization can survive in the presence of long-range interactions or not. So with this, I think I would like to conclude. So I hope I have convinced you that condensed matter physics is the subject one should go for, and it is full of excitement. It has very exotic phases, lots of interesting phenomena, and I just try to tell you one of the interesting phenomena that I'm recently working on, and it's called many-body localization. It's really a big puzzle. It's a very peculiar, it's a very unusual phenomena, and it's full of questions, okay? We don't know in what kind of system it exists, what is the nature of the transition, how stable it is, and if you attach a bath to that system, what will happen? So basically, we only know the questions, and we have very few answers. So all of you are welcome to join us. Thank you for your attention.
Okay, so we have a few questions, but time for some more questions.
Or Arti? Yes, please.
Ma'am, hopping is due to repulsion, right?
No,
So
no, no.
why they are both different?
So hopping basically means, so every system will have some hopping for electrons. So that's the kinetic energy part of your Hamiltonian. So electrons can move from one side to another, right? And repulsion is the potential energy part of your Hamiltonian. There can be a repulsion, there can be attraction between the fermions, right? So if there is more kinetic energy, it means particles are able to go very far from where they are starting, that will help them in delocalization. That's what I'm trying to say.
Any other questions?
Yes, Anish. Any others will begin with this thing? No? Anish.
So as you said that the diffusion constant is always 0 in those quantum random walk models. Is it valid for all?
Not always. I said
Yeah.
dimensionality plays a crucial role. So if you are in 1D and 2D, it will always be 0. In 3D, there is a metal to insulator transition. So only if you are in Anderson localized phase, it will be 0.
Okay, so specifically, which kind of quantum random walk model you are suggesting? Like,
Which kind of random
Yeah.
walker? So I'm calling it a random walker, but actually the kind of, let me show it here itself. If you forget about the third term in this system, right? In
Yeah.
this model, the kind of model I'm talking about is very simple. You just have, say, hopping of some quantum particle in your lattice, and at every site you have a random disorder potential. Okay, which is enough to provide inhomogeneity in the system. And in this kind of system, you can see localization.
Any other questions? Yes,
Yeah.
someone. Yes.
The poster for your talk had this picture, which you also showed in your slide, of particles moving around and a quasi-particle.
Yeah.
So can you explain the
So
connection of
those-
this picture with many-body localization?
Oh, that picture is, I don't know which picture I gave. Actually, there is one picture like
I'll
this.
remind you when you come to it. Just
So
go
if
back.
you look at one
No,
of these particles, the blue one is basically a quantum particle, and the black crosses are the impurities. So my particle is going around and hitting the impurities. That's what I'm trying to say. And if you have many blue dots, it means that you have many quantum particles in your system, and you also have lots of impurities.
Okay.
So now you have interaction as well as disorder in the system.
So the picture on your poster was maybe a few slides, couple of slides earlier. It had something also named as a quasi-particle, some green circle.
This
Yes,
is.
the next one.
Yeah. So here I'm just putting a red circle on that, calling it a quantum particle. It's the same picture basically. This is for one quantum particle in the presence of lots of impurities. And that one was many quantum particles in the presence of lots of impurities.
Any other questions? Yeah, please.
There's a question, yeah? I'll come. Yeah, go ahead.
Hi, so I always have this question that what do you exactly mean that they have coherent motion? Like I have asked many people, but I've not really gotten an answer that kind of satisfies me.
Okay. So to start with, I can give you a very simple analogy. Suppose you think of vectors, some spins, right? So you may have all spins aligned in certain fashion, or you may have just random orientation of the spins. Okay. So when you have spins aligned in certain fashion, that is one way of saying that the system is coherent. And I can do the same thing with these Cooper pairs, because for Cooper pairs, I have a wave function, right? And every wave function has a real part and a complex part. So it has a phase part. So if there is a phase synchronization, if there is a phase coherence, I call it a coherent state of Cooper pairs. Okay, so that phase coherence can be found analogous to these spins which were already there. So Cooper pairs are already there, just like spins are already there, but spins may be aligned or may not be aligned. So if spins are aligned, that is equivalent of having a phase coherence of Cooper pairs. Okay, but Cooper pairs may be out of phase with each other. They may not be obeying the same phase.
Them being in phase is leading to these memory effects.
Yes, you need basically a global phase for your wave function to be in a superconducting phase.
There was a question. Yeah.
Ma'am, can you please repeat that part where we can find out from the distribution whether it is localized or not?
Distribution. Which distribution?
Probability distribution.
Yeah, sir.
Just stop me where I said this.
Arti gap studies like that. The Vigyan.
Oh. This one?
Yeah.
Okay. So you have this many-body Hamiltonian, which is disordered and interacting, right? You can write down the Schrodinger equation for this in time-independent Schrodinger equation and get the eigenvalues. Okay. Now, if you look at what is the difference between consecutive eigenvalues, You have to arrange them in certain fashion, ascending or descending order. And then you look at the spacing between the consecutive eigenvalues. Okay. So now since your system is disordered, that spacing will not be same for every eigenvalue, right? It can be something here, it can be some other number there. So if you look at the average value of that spacing, or you can also calculate the probability distribution of that spacing. You have a random variable now, you can find out the probability distribution corresponding to it. So what you will find is that if the system has weak disorder, right, then there is the probability of having zero spacing is zero. And as the spacing increases, the probability also increases. This is what is called the Wigner-Dyson distribution. But when the disorder is very, very strong, then the probability of having zero spacing is finite. And as you increase the spacing, the probability reduces. This is the Poissonian distribution. Okay.
Yeah.
Ma'am, what are the possible uses of many-body localization? Like, can they help us probe some different properties because of the
That's
ergodicity?
very interesting question. Okay, so it's always good to think whether what we are studying has any practical applications or not, right? That's what you're asking. So first of all, I will say conceptually it is very interesting because anything which challenges the theoretical tools that we already know is good because it helps in developing more theoretical tools, right? Now coming to the application point of view, so I think we are still lagging behind there, but I can tell you where it can be useful if we really realize it in many, many systems. Okay, because this is a system which is not going to thermalize so easily, or it cannot decay basically, where whatever state you prepare it in, it will kind of remain in that state. So it can be very useful, you know, because when we in quantum computation in future. Okay, I'm not sure whether we will be able to use it or not, but anything which has a very poor decay is generally very good for quantum computation.
Thank you.
And
Ma'am,
go ahead.
what is the meaning of half metal and symmetric breaking?
Okay, very good. So half metal we talked about. So metal, you know, right? So if you think of a system of electrons, right? Electron is a spin half particle. And where did I talk about? Yeah. So electron is a spin half particle. So there are two possibilities for the spin. It can be up or down if we think about the Z component of the spin of the electron, right? So generally in a metal, when we say that the system is conducting, electrons with both the spin polarizations are conducting, right? But it can happen that the two spin species of my system face very different environment. My lattice can be such that suppose my lattice has two types of sublattices which are interpenetrating. Okay, most of the upspin particles live on one sublattice, most of the downspin particles live on another sublattice, and then it can happen because of the interactions. I make only one of the spin channel insulating, and the other electrons with the other spin may remain conducting. Okay, so now I can have a charge transport only through, say, upspin electrons. If the electron has a downspin, it will just remain insulating. It will not be able to conduct. This is called half metal because only half of the degrees of freedom are contributing to the conduction. Any example? Oh, Razib, do you often remember any example? So there are some complicated materials you won't be able to recognize the names. These go under the name of half Heusler alloys and all. So there are actually lots of materials which undergo the name of half metals. And interesting thing is most of them have a very different mechanism than what I'm trying to tell you, because here I'm trying to tell you even interactions can make something half metallic. Okay, but we don't have many examples of this. But we have lots of half metals. Half metallicity can come because of various reasons. Okay. Yeah.
Can you explain localization of states in simpler words? Like, is it anything related to confinement or?
It is like confinement, but it is something more than confinement. Okay, so basically, confinement will mean that suppose you are in an aeroplane, when you are confined in your seat, right? You are not able to move. But what I'm saying here is that there is certain, suppose if I draw the wave function of like this, okay, this is my mod psi square, and this is x. So I'm saying my wave function is peaked here, and then it decays exponentially on both sides, okay? But within this length scale, my particle is allowed to move freely. It is not confined. It has a finite localization length, which is much smaller than my system size. That is why it will never be able to reach other end of the sample if I pass a current through my system, if I apply a voltage to my system. So it will not be able to conduct charge. But it is not confined in the sense that within this localization length, it is moving as freely as any other particle in my system. Okay, that's the difference from confinement. It would be confinement if it is not at all able to move. Okay.
So your example, the confinement is a takeoff of the place. You are staying in the place.
Yeah.
But localization is you're free to move in the economic.
Right.
Well, economic events don't have much space, but okay. Any other questions from students? Of course, you will have an interaction session with Arti where you can bug her with more questions, and like you can also ask her for some formula for half Weissler alloys, which I have forgotten. She has forgotten, and they're complicated stuff, but she can look it up for you. Any other questions on the top? Okay, then let's thank Arti for a very nice talk. It was very interactive and so on. And I would hand it, tea in the canteen. Okay, so you all of us can join for us for tea in the West Canteen. I think you have already been to the West Canteen, so we'll have some tea and snacks.